Hi, welcome to our podcast. Today we will be discussing physics seen in dance. We will evaluate what is essential for proper balance, turns, jumps, and all elements needed to make an exceptional dancer. Vocab that will be used throughout the lesson include velocity, which is the rate of change of the displacement, the difference between the final and initial position of an object, momentum, which is the quantity of motion of a moving body, force, which is any interaction which tends to change the motion of an object, angular momentum, which is the rotational analog of linear momentum, centrifugal force, which is an apparent force that acts outward on a body moving around a center arising from the body's inertia, and torque, which is a twisting force that tends to cause rotation. Now we will be discussing turns in ballet. If a ballerina wants to spin faster, she must decrease her rotational inertia and thereby increase her angular velocity. If the ballerina wants to spin slower, she must increase her rotational inertia and thereby her angular velocity must decrease. Rotational inertia is measurement of how hard it is to start spinning something. In terms of calculating the rotational inertia, it is crucial to remember that the greater the mass, the greater the rotational inertia. As the mass gets farther from the rotation axis, the rotational inertia also gets larger. Additionally, torques cause something to spin as they are off-center forces. Torques also change angular momentum. The harder you push, the more quickly the object spins up. The further from the spin axis you apply the forces used to generate the torque, the more quickly the object spins up. The longer you push, the greater the total change in angular momentum. If no torque is applied to a rigid object, its spin axis doesn't wobble. Therefore, it spins at a constant rate. Greater angular momentum makes it harder to stop. Now we will talk about turns in terms of breakdancing. In breakdancing, a headspin is a basic power move, a move requiring tremendous strength to complete. Headspins are performed by engaging in a handstand, then lowering the body such that the head touches the ground. The breakdancer then lifts their hands and pushes off, causing rapid spinning on his or her head. The breakdancer stretches their legs as in the splits. By contracting or extending his or her legs, a breakdancer can make a headspin go faster or slower, respectively. This relies upon angular momentum and moment of inertia. Momentum measures how likely an object will change in position along a straight path at constant speed. Angular momentum measures how likely an object will spin. It correlates the mass and speed of the object to the radius of the circular path. Angular momentum is constant unless torque is applied. It can be used to measure torque applied to an object over time based upon differences between initial and final angular momentum. In the case of a breakdancer, there is a friction force decelerating the headspin. The harder the breakdancer pushes off the floor, the more rapidly the momentum changes. The longer they push, the greater the total change in momentum. If the breakdancer does not push on something while they are spinning, their speed nor their direction of travel will change. However, greater momentum does make it harder to stop. If they do push on something while spinning, they can change their speed and or direction of travel. To help you better understand the vocabulary, I will go over some analogies. It is called velocity when there is motion without spins. It's called angular velocity when it's motion with spins. It's called mass when it's motion without spins, and rotational inertia when it's motion with spins. Momentum, motion without spins. Angular momentum, motion with spins. Force, motion without spins, and torque, motion with spins. A force is a vector quantity, meaning that it has both magnitude and direction. There are three forces that act on a dancer. Gravity, which is downwards, support from the floor, which is upwards, and friction from the floor, which is sideways. Friction is the force that resists relative motion between two bodies in contact. Now, you may be wondering how a dancer maintains its balance. Well, first of all, what is balance? This means no total force and no total torque when the dancer... Now, you may be wondering how a dancer maintains his or her balance. First off, what is balance? Balance is no total force or no total torque if the motion includes spins. If the dancer is standing, no total force is needed so that the momentum does not change. However, if the dancer is spinning, no total torque is needed so that the angular momentum does not change. The center of gravity is also an important aspect in maintaining balance, as it is that point at which the object will balance. In order to stay balanced, the center of gravity must remain directly above the area of contact with the floor. Then, gravity's downward push and the floor's upward push will go through the dancer's center of gravity, and there is no total force and no total torque. Therefore, balance. Now we will discuss jumps as relates to ballet. Gravitational force plays a major role in jumps. The total effect of gravity is the same as if it were acting on the dancer's center of gravity only. Gravitational force is proportional to an object's mass, so double the mass and the gravitational pull will double too. Finally, gravity only affects vertical, not horizontal motion. Vertical motion is the parabola that is created when a dancer goes up and then comes back down. This can be described as a center of gravity versus time. Jumps can also be explained not only using gravity, but also Newton's laws. Specifically, his third law states that for every force that acts on an object, there is an equal and opposite reaction force acting on a different object. This means that when the dancer pushes off for a jump, the floor exerts a force equal to that of the dancer. When a dancer jumps, he or she creates a parabola. In physics, we call this a projectile. A projectile is defined as an object that has been set into motion by a force and follows a path that depends solely on the acceleration of gravity. The acceleration of gravity is a constant for any object under gravitational pull. So, g equals 9.8 meters per second squared. To understand the principles of projectile motion, the center of gravity of the dancer must be treated as a single point. A dancer can intentionally change the shape of their body while in the air, unlike a simple object such as a ball. This leads to many interesting results. We must note, however, that once the dancer has left the floor, the center of gravity will continue moving in a trajectory path that cannot be changed in midair. The dancer is experiencing no acceleration in the x direction, vertical motion, and a constant acceleration of 9.8 meters per second in the y direction, horizontal motion. Therefore, gravity only affects vertical, not horizontal motion. The radius is the distance from the point around which the object spins. In the case of a breakdancer with legs fully extended, this would be the distance from between his or her crotch and toes. For an object with constant mass rotating in a constant path, the angular momentum is the product of the object's moment of inertia and its angular velocity vector. If the person bends their knees to cut split the length of their legs, then their radius is cut in half. As a result, their velocity doubles. Friction will require the breakdancer to eventually apply more force to maintain high speed. However, by pulling in his or her legs, the breakdancer will be able to move faster with much less force. This is due to angular momentum. So, by decreasing radius, linear momentum increases to maintain a constant angular momentum. Since the person does not get significantly fatter while breakdancing, their velocity and radius, linear momentum increases to maintain a constant angular momentum. Since the person does not get significantly fatter while breakdancing, their velocity must increase to accommodate a constant angular momentum.